And by the way, the midterm grades are out. You'll see them in Canvas. There's no midterm exam. I just added up all the homework and discussions and quizzes and stuff and made a total and made a percentage out of it. There's a lot of extra credit, so an awful lot of people got A's. If you've been doing extra credit, you should probably have an A. Anyway, the midterm grades are in there, and I'll submit them to the City College system in the next few days. So we're down here at keyed hashing. So let's take a look at that. All right, so we're going to talk about message authentication codes, which act like signatures on a message, and pseudo-random functions, which are closely related mathematically, and then keyed and unkeyed hashes and block ciphers and the usual stuff. So a keyed hash. Now anybody could make a hash on a message. You could just calculate the MD5 or the SHA-1 or something and attach it to the message, and all that would do is detect it if the message has been altered, which is simple integrity in security speak. That's confidentiality, integrity, and availability are the three aspects of security, and you get integrity from a hash. If the hash matches, the file has not been altered. But that does not count. Now what you'd like here, though, is you would like authenticity and integrity. You would like not only to know that the file has not been altered, but you'd also like to know that the file in fact comes from a certain person. And that's a message authentication code. So what you do is you include a secret key and the message and calculate a hash from it. And therefore, when you recalculate the hash and the hash matches, that proves both that the message has not been altered and that it came from the other person that has the secret key. So now you have authenticity and integrity. So that's a good thing. And you call this thing a tag instead of just calling it a hash. It is a MAC tag. All right. So it's used in a lot of systems. IPsec, SSL, SSH, TLS. It's not used in 3G and 4G telephony. They do encryption, but they don't bother to add message authentication codes to the packets. And this means an attacker can modify the packets, and it will not be accepted as a corrupted packet, so you can cause static on the line. If you had a message authentication code on every packet, then a modified packet would fail that test and would not affect the sound, presumably, except perhaps by some kind of delay waiting for a replacement packet. So here's the various things that can go wrong. A forgery, for example. I should not be able to create a valid tag without knowing the key. That's the whole point. So if I'm able to forge a message, I should not be able to also forge the tag, and therefore you'll be able to tell authentic messages from fake messages. So it's unforgeable if you cannot create a forgery. Now there's known message attacks. This is the simplest one, where you just passively collect messages and tags and try to find the key. This is essentially the simplest web attack, where you just collect packets off the wire. A chosen message attack is the standard one they use, which is even stronger, where not only can I observe messages and tags, I can send in messages, and it will calculate the tag, and I can read the tags, and I'm allowed to make as many of those as I want and see if I can deduce the key. And of course, I could then choose carefully crafted messages, which when turned into a tag might leak out information, like perhaps the message that's all zeros might tell me something. The message that just has one bit somewhere might tell me something. Might be able to carefully craft messages that will give me information about the tag. Now, one thing about them is replay attacks. Clearly, you've got a message and a tag. I could just record it and replay the whole thing. And of course, then it would pass the test, saying this is a valid tag, so that's a problem. And this is, I was talking in another one of these classes recently about keyless entries into cars. And of course, that's a problem there. Now, what they do with most cars is they have a sequence of messages. So you can't use the straight replay and play it again. They solve it this way. There's a pattern, and they won't accept the message a second time. So it's got a message number in each message. And if I just got message number 100, and later on somebody sends me another message 100, I won't accept it because I'm keeping track of the number, and I only want to hear a message 102 and then a 103, something like that. That's one way to do it. And that's what cars do, at least the cars I've read about. So then there's pseudo-random functions we've talked about a lot. So I'm going to just create apparently random bits. And this is what key derivation schemes use. We've talked about PBKDF2, password-based key derivation functions, where you start with a password, and then you turn it into a apparently random series of bits. See, I think with a lot of keyless signals, only a certain number of those messages sort of loop around. Yes, that's true. And they say they do Ford and the Jeep? Yeah, I don't know. Are they particularly insecure in the lock, or is it just that they don't work very well? I tend to stay away from American cars. All my life it's been a truism that American cars will break down all the time. But anyway, so if you have a key and a message, so the output looks random, but it's not random in the sense that if you feed in the same message again and the same key, you'll get exactly the same answer. It's like a hash that way. Anyway, this is the way they take your password and turn it into something like an AES key. All right, so 4G telephony uses these to authenticate a SIM card, and TLS uses one of these to generate a key material from a master secret. So, it is a way to just take some data that is in some structure that's not convenient, like an alphabetic password, and turn it into a cryptographically convenient number, like a series of random bits, 128 bits long or something, to use for an AES key. That's all it is. And so you'd like your pseudo-random function to look random, be indistinguishable with statistical tests. Oh, Jeep was found to be the most hackable car. Oh, that's fun. Okay. And therefore, this is fundamentally stronger than MACs. A MAC has to be unforgeable, but it does not really have to appear random. So if something is a good PRF, pseudo-random function, then it would also be a good MAC function. So to take unkeyed hashes and turn them into keyed hashes, you could take something like SHA-1 or SHA-2, and you could include a key by just adding the key to the message. So take the key and then add the message after it. That would give you something that depends on both the key and the message, but the problem is you might be vulnerable to a linked extension attack. If I have the tag for this message, I could add more text to the message, and I could calculate the valid tag for the longer message. So that's not good. And as we talked about before, SHA-1 and SHA-2 are both vulnerable to that because they have this iterative process of adding blocks, and they are vulnerable to this, but not SHA-3. And another issue is you didn't put a delimiter between the key and the message. So if I had a key of 123 ABC and a message of DEF000, or a key of 123A and a message of BCDEF00, they would both hash to the same thing, because you haven't in any way just marked the difference between the key and the message, and that's kind of sloppy. So you could have a hashing routine like the modern ones that actually include a way to insert the key. So you don't mix the key in with the message, you feed the key in separately, it's handled separately, which is a good answer. Or another one would be to include the length along with the key. That would help. All right. And so another way to do it would be to just put the key after the message. Take your message and add the key at the end. Now you can't do a length extension, because if you try to add more message after that, you're really not getting what you need. What you need to get a valid key would be message 1, message 2 key, but you're getting message 1 key, message 2. So that will prevent the length extension attack. All right. But it doesn't solve that other problem where you still can't discriminate where the message stops and the key begins. All right, and if there's a hash collision, then you, of course, have a tag collision also. So there's HMAC. This is the construction to try to solve all these problems. And this is the standard. It's been approved for a while. And what you do is you do this sort of complicated mess. Instead of just putting the key in once, you put the key in twice before the message. You put the key XOR with this OPAD number, which is just a bunch of 5 seeds. And then you take the key and XOR it with IPAD and take the hash of that with the message, and then you take the hash of all that. So this way you've added the key in twice, once hashed and once unhashed. You've hashed the whole thing twice. And this thing, there's no way to hit it with a linked extension attack or pretty much anything. That's the idea. This way you've mixed the key into it in a way that is not too expensive to calculate and very hard to find a way to forge a message once you've done all that. So now you got to choose a hash function. So you could use, for example, SHA-256 if you want to. And then this is how it would look. You XOR the key with the input pad and then feed in a block and compress it. and then that forms H1 prime, which you compress with the message. And here you have the output pad that goes through a different series. So, it's the it's a few steps, but it's not too complicated to do. So if you want to break that, you pretty much have to just do a brute force attack. The way to do it would be to try to find a hash collision. So you're going to have to do 2 to the n over 2 calculations, where n is the length of the digest, before you can find 2 messages that hit the same hash, the same tag value. You don't need a length extension attack. Of course, anything will fall for this. This is essentially a brute force attack. So the only cure is to make the hash value long enough that the square root of the possible number of hashes is too much big a number. So you got to have n larger than 128, so that 2 to the n over 2 is bigger than 2 to the 64. And as I think we said, the largest brute force attack ever done is 2 to the 72. I think it might be 2 to the 64, and 2 to the 72 is still in progress, something like that. So anyway, that's the point. All right. And so that's the idea of just trying them all until you find a real collision. So that's quite impractical as long as you have 128 bits or longer hash. All right. So let's take a look at some Cahoots. Guess that'll do. All right. I'm going to go turn on the light. Looks like that's it. Let's go ahead. All right, which system has no MAC? All right, that's 4G, good. All right, which one is most successful against a MAC? They're intrinsically vulnerable to replay attacks. If you replay the same message, it has the same message authentication code. There's no randomness or anything. Which one is not vulnerable to length extension? SHA-3, yep, everybody knows that, good. All right, which one is vulnerable to length extension? Secret prefix. If you have the secret and then the message, you can just add another message. Now you've got secret message 1, message 2, which is valid. So that's the flaw. Putting the secret at the start creates length extension vulnerabilities. All right. All right. I think I know who that is. And I know who that is. All right. All right, good. 6:30, we're right on track. So, all right, so you can use block ciphers to make these, and we talked about this before. One easy way to make cryptographic objects is to just reuse existing cryptographic objects that you know their security properties. That's a nice way to go, although it's probably not the most efficient way to accomplish your goal. It certainly is an easy, simple way to do it. So you can take a block cipher, and a lot of hash functions are in fact made from block ciphers. And here's a couple of slides from a previous chapter about this. You use the Merkle-Damgard construction. So this, you have a compression function, and you can make the compression function that combines a block of message with the previous hash value that came in and gives you another hash value coming out, and you can just use a block cipher and take the blocks of message and use it as a key, and then use an encryption routine and combine it with an XOR process so the decryption won't work. This is how you take a block cipher function and use it to create a compression function to be one round of a hash function. And that's perfectly fine. But all right, so that's what happens. All of them are built on a block cipher. CMAC uses only a block cipher. Not as popular as HMAC, but it is used sometimes. And so it's CBCMAC. This is incredibly simple. Remember, cipher block chaining, you feed in an IV, which in this case you just set to 0. Then you encrypt a block of text. Then you take that output and use it as the IV for the next one, and use that as the IV for the next one. So this is the ciphertext that could be decrypted, but in this case, you throw everything away except the last block. The last block now depends on everything, not just the last block of plain text, but all the previous blocks of plain text were involved in the IV. So if you throw away everything except this block, then there's no way to decrypt it, and you've got a hash. So this is a way to create a fixed length output that depends on all the input in a reversible way, so there's nothing terribly wrong with it. The only thing that's wrong with it, as you might imagine, is this is a whole lot of unnecessary calculation to achieve the goal. It's not the most efficient way to do it, but all right. Now, if you're going to break it, suppose you have 2 messages and 2 tags that you know about, and they're single block messages. Then you could create the tag of this message, because you have the fundamental problem here, which is the same thing that led to the attack we had against CBC before, the padding oracle. This part here, where you just take the output of this block and XOR it with the plain text here, that is an excessively simple operation. And if you can find a way to attack that, you can break it. And so here, if you have 2 tags you know, then there you can figure out what message also has tag 2, and that's this one, M1 appended with M2. The 2 blocks here, you take M1, and you know this will make tag 1, and tag 1 is used as the IV for this part. So you can construct a message, another message that will match the first one of the tags. So you can forge a message tag combination that is more than just a simple replay attack, and that's a weakness of the system. It is possible to forge a valid message. They call that existential forgery. You can forge a message. You can't exactly control the contents of it in any great detail, but you can create a new message from other messages that will pass the test, and that's not a good property. You haven't achieved the fundamental property we said from the start. The whole idea is nobody should be able to make a valid tag except the authorized user. And you can, in this case, make a valid tag without being the authorized user. So if you want to fix it, instead of using one key for every encryption, use the key and generate 2 keys from it. And then use a different key for the last encryption. And now, even if you know the tag from one encryption, you won't be able to use it for another. And so here's the game. What they did is if the message fills the last block exactly, then you use K for every step, but you use K1 for the last step. And if you have to pad it, then you use K for everything and then K2 for the last step. And that turns out to be quite effective at preventing you from combining tags from messages you see to generate a new message with tags with a valid tag. It's very much like the sort of thing we've done before to prevent length extension attacks. Just making the last step different is enough to mean you cannot create a valid hash by adding more to an existing one. All right, so here's some designs. These use hash functions and block ciphers to build pseudo-random functions. Does it matter how you generate those keys? it's a very good question, good word, and I imagine it does. As I imagine if you did something really, really simple, like just add 1 to make the new key, that would be a problem. So I assume you do something a little more complicated than that, like run it through a hash function or something to scramble it. But I haven't seen any description of how you generate the keys. There is a key schedule in AES too, and I'm sure you have to put a little thought into generating those keys so that they're not too simply related to each other. But I don't have exact knowledge of what you do. I'm sure it matters. And I would imagine what you want is to make it fairly random, where all the bits tend to be different and you can't easily deduce one key from the other one and things like that. It's a good question, though. I know if you think about the IVs, the IV can just be counting, and that's fine. It might be okay to just add 1 to the key and add 1 again for all I know, but I imagine you do something a little more clever than that. All right, so you can make functions that are designed specifically for making a MAC, and the point is they don't really need all the mathematical properties of these encryption routines. You could have a simpler function that's good enough for making a MAC, and then it would be faster. So, if you want to make it efficient, this is Poly 1305, designed to run fast and used by some modern tricks, modern protocols. And so this is a universal hash function, which apparently is not collision resistant, but it turns out that doesn't matter because you're using a secret key, I guess. And so you can, the only 2 security requirements are that you cannot find a collision for a random key. And so you can make this so you can't find these collisions, whereas without the key, you could find a collision, and that's good enough for the purpose we're using. And it also doesn't need to be pseudo-random. There can be patterns in the bits, we don't care. All we really need is just that you can't find a collision so that this tag will match a second message. So they were able to make a very simple one that's just a polynomial expansion. Just you have R as I think a random number and then a key, and or like a nonce or something, and you just take this M1, M3, Mn, on you go. I wonder if that should be an M2, but anyway, you just add powers of the key. Key squared, key cubed, up to key to the n. And that's the game. So you can, this turns out to be something that's fast to calculate and simpler than the other hash functions. So you can do that. You can build a MAC from a universal hash function and a pseudo-random function and 2 keys, and this turns and a nonce, and this turns out to be fast to calculate and good enough. So it's secure if you have a universal hash, a pseudo-random function, and you don't reuse the nonce. And the output is, of course, long enough that you can't brute force it. So longer than 128 bits, like we said before. All right, and so here's another one, Poly 1305 AES. Includes the same poly, and then you do 1 round of AES. So this is another way to do it, and this proves that it is secure as AES. Now you've added all the security of AES to it by only having to encrypt 1 block of AES instead of having to encrypt a lot of blocks like CBC. So it's just a way to gain all the mathematical desirability of AES without putting a lot of extra processing cycles in it. And then there's SIP-hash, Poly 1305. The whole point of all this nonsense here is to handle a long message, where you have block after block and you're using a simple calculation so you don't have to do too much calculation on it. But if you had a short message that fits in 1 block, then there's a thing called SIP-hash specifically for that. And SIP-hash is uses just XORs and additions and word rotations with these rounds. A 15-byte message just showing various constants feed in, various pieces of key and various pieces of message going in. And it's just designed to be really fast. So, this is the point. We had some old algorithms that were designed for encryption that we reused and they're safe, but if you could refine them by keeping only the desirable mathematical properties and removing all the unnecessary operations, and you could still have security with less cycles. That's the advantage of these more modern encryption routines, which is why, most people just don't care. Like I said, most people are still using things like RSA, because all you really care about is that it works. and you don't really care about wasting a little power and stuff. But as people move to phones and mobile devices, and they really do care about wasting power in CPU cycles, then it's good to move to more modern encryption routines like ECC and these things to get the properties you need without wasting power and cycles. So here's some things that can go wrong. Side channel attacks, of course, are always there. Any mathematical operation, there could be some way to, when you realize it in physical hardware, the key could leak out somehow. Here's a very common one. You're trying to compare two numbers to see if the key matches. If the MAC matches, you can compare the first byte, and if it doesn't match, you're done. If it does match, you try the second byte and the third byte. Well, that means the time it takes to compare the MAC will be different if the first byte matches and if the first byte doesn't match. So by measuring the time for the comparison, you can deduce something about it, and that's not good. So the solution is to write inefficient code that always takes the same amount of time, that never takes any shortcuts. So instead of doing this, comparing it byte by byte and leaving as soon as a byte is different, you would compare all the bytes. And you'd have something like a Boolean value that as soon as one byte is different, you mark it the Boolean value false, but you go ahead and do the calculation on all the others anyway that you don't have to do and return false. That's one way to go. And then remember, the sponge function, like used in SHA-3, has this internal state. Yes, very point, good word. That's why these side channel attacks are murder, and these timing attacks are murder. It is really hard to write code that is not vulnerable to those things. It's one of the fundamental problems in cryptography, and this is why you never should write your own crypto. You should always use a standard library like Sodium, where other people have put in the work to make it really resist all these attacks. And they're not perfect either, but at least then there will be updates and stuff for it. Whereas if you write your own stuff, it tends to make a really stupid mistake and be that way for years, and that's how people keep having security disasters. Anybody that writes their own crypto usually creates a disaster because there are just so many picky little things. It'd be better to just connect to a main branch. Reminds me of a discussion I've had in a lot of my classes about operating systems. Like there are some people, like Cisco, that write their own operating system, iOS. They don't use Linux, and they don't use Windows. And I was thinking, if I was running a company and my engineers said, we're going to write our own operating system, I would say, why don't I just fire you? Because whatever you're doing, you could do it with either Windows or Linux. How could you possibly need something other than that? And if you really do, you've created a huge burden on the company. Now I have to keep all the patches, drivers, and everything. How could it be that you can't find some standard version of Windows or Linux that will do whatever you're doing? Certainly, that would be my recommendation for anything. Connect to a established chain of code that's maintained by a user base and save yourself all that effort if you can. Anyway, so the internal state of these sponge functions, like SHA-3, it's got an internal state, it takes and it mixes in bytes of the message, and then you take some of those bytes and call it the hash. So if you were able to get the internal state by leaking out electronic emanations or something, then these things might fail. You'd be able to forge them, but apparently the compression function-based MACs are not vulnerable to that. Even if you were able to read the internal state of the sponge, you wouldn't be able to forge it. So that's a nice thing to know. That's why I say these modern algorithms are designed to resist all known attacks. And remember, this happened in the history of, I think it was SHA. SHA-0 came out, and the NSA told them, no, you have to change it to SHA-1 without explaining it, because there was a secret attack that only the NSA knew about that would break it. And they fixed it, so it was no longer vulnerable to that, but it was like 20 years before anybody figured out why. So this is why you keep having to update your cryptography. All you can do is make it resist all the attacks you know of now. And a few years later, there's a new attack, and now you need to change your algorithms to resist that new attack, and this just seems to never end. So, and that, of course, to be fair, is why Microsoft wants everybody to update their hardware, because if you run Windows 11 on new hardware, you can use the latest versions of all these crypto functions, and if you run it on the same old hardware you used for your Windows 10, then you can only run the older version of the algorithms, which is technically not as perfect, but in practice fine for most users. All right. Is there a backup for public key crypto? Oh, yes. Yes, there is. And we'll be talking about it a lot more later. In fact, RSA is likely to become hackable by quantum computers. And there is a competition going underway right now to pick the replacement. There's several dozen algorithms being considered. I think it's windowed down to about 5 now. Absolutely. There's a whole new generation of public key crypto coming, and we'll go through it in detail later in the course. Yeah. Not only RSA, but ECC and everything we're currently using is expected to fall in about 20 years from quantum computers. So we are already generating the new ones that even quantum computers can't crack. The one that I was betting on was Google's New Hope, but that has already fallen. So I figured I better wait until they make up their mind before I start writing projects. I was all set to write New Hope projects, but that would have been a mistake because New Hope has fallen out of favor. Anyway. All right, a hash function that is not collision resistant. The UHF. It's only collision resistant when you have a key. Use it without a key, you can find the collisions. All right, which system is fastest for long messages? That's this Poly 1305 AES. All right. All right, which one is best for small messages? SIP hash. Good. And which one uses a block cipher, but only for one block? Yep, this one here, one block of AES. So you get the mathematical benefits of AES without having to do too much extra calculation. All right, I know who that is. And that also. Ah, well, same winners both times. All right, good. So I've got that recorded. Let me stop this recording.